I'm Harry Atwater from Caltech. What I want to do is to take on the daunting task of identifying some key issues associated with thin film photovoltaics over the next few minutes to frame some of our discussion going forward today. And I want to thank some of the contributors to the work that I'll show here: Dave Ginley from NREL, Richard King from Spectralab, Martin Green, Jeff Portmans from IMEC, and students Mike DeSegli, Greg Kimball, and Vivian Ferry from Caltech, and Albert Pullman from the FOM Institute. And this backdrop to my first slide serves as inspiration for me and hopefully for all of us here, given the large scale of electricity consumption and generation that we're addressing ourselves to. So I wanted to start just looking at a purely financial picture of photovoltaics. And I think it's illustrative because so far we've been talking about crystalline silicon and fundamental issues associated with photovoltaics, which have been applied quite straightforwardly, or not straightforwardly, but comprehensively to crystalline silicon and to a few other semiconductors. And yet, in the last few years, there has been a remarkable growth in the marketplace of thin film materials like amorphous silicon, copper, indium, gallium diselenide, and cadmium telluride thin films. And one of the reasons for this, I think you can see perhaps on this curve, as was pointed out by the previous two speakers, the efficiency of these technologies is nowhere near at least nowhere near the Shockley-Queisser limit, and nowhere near the discrepancy between the Shockley-Queisser limit and the simple considerations that we've been talking about so far. Nonetheless, one of the things that is compelling about the thin film technologies is the initially lower cost. And this gentleman with whom I had a discussion from Deutsche Bank, he's an investment analyst. He is innocent of and suffers no prejudice by direct technical or scientific knowledge about the materials. And so he looks at things only from the point of view of cost. And so the story on this chart, which shows the grid price for solar PV in cents per kilowatt hour, illustrates the advantage, at least at the moment, or the attractive features that are at least available at the moment for some of the thin film technologies. And for example, it was brought up earlier that First Solar is an attractive stock, and this is one of the reasons why. Because of as a public company, they're required to divulge their financial data and costs, and indeed, they are, by acclaim, the lowest cost per watt manufacturer of photovoltaics. And what that means is that as costs decline, and you can see here we're really at a tipping point in photovoltaics where the cost of electricity is approaching the cost of grid-connected central utility plant-generated electricity, which of course for the most part is a mature industry, and barring dramatic breakthroughs in efficiency, are likely, because of the fuel costs and other associated regulatory costs, if anything, to go up in price per kilowatt hour rather than down, unlike photovoltaics. So it seems axiomatic that at some point these curves will cross, and then it's really a matter of just where they cross and when. And one of the things that's interesting about this is that in the eyes of many who look at this, who are at least those who are associated with thin films, but also who are investment analysts, they see this happening first for the thin films because of the lower cost per watt. Yes? Yes. Right. Yeah. Yeah. Well, right. Yeah. Well, and this maybe C refers to conventional silicon, or silicon that doesn't have the that has some of the planar contacts and features that prevent you from accessing the high efficiency features. Yeah, that's right. Yeah, thank you for pointing that out, Dick. So here, good thing I had a straight man in the audience here for high efficiency. But you can see that these are projected to be, remarkably competitive. And that, by the way, that illustrates what is going to be the point on my last slide, which is that efficiency. I'm going to echo the sentiments of the previous speakers that efficiency is really paramount. And so, if we look at sort of intercomparison, this is some broad intercomparison of efficiencies for a variety of technologies: dye-sensitized solar cells, which are inherently thin film, amorphous silicon thin films, cadmium telluride thin films, copper, indium, gallium diselenide thin films, and wafer-based multicrystalline or monocrystalline, and then high performance, which is the type of material that Dick was talking about. And in general, there's a discrepancy, in some cases quite large, between the champion cells that have been developed in the laboratory and the module efficiency that have been achieved. And many of those have to do with microstructural features, either on the scale of the difference in scale between a champion lab cell and a module, or even at the microscopic scale. So one thing I also wanted to sort of, just for the benefit of the students, is to talk about, very often in the field of photovoltaics, people are asked, and if you're ever asked about energy payback times, this is now somewhat dated, but at least gives some ideas that the energy payback times are certainly quite attractive, and as energy costs are driven out of the photovoltaics process, the energy payback times are of the order of a few years, and perhaps anticipated to drop to as low as a year or below. It's a very interesting number, because then one can imagine that the growth in energy consumption in the photovoltaics industry associated with manufacturing with rapid growth would not be a huge impact. And this is, of course, very attractive given a conventional module lifetime and system life of 30 years. So one of the things I wanted to start with was a view that allows us to perform an intercomparison of crystalline silicon, thin film, and other technologies. And this is a map that was first designed by Martin Green. And it's a map of efficiency versus cost per unit area for photovoltaic devices, conventionally thought of in terms of generation 1 crystalline silicon photovoltaics, generation 2, which is generally thought of as being thin films, and exotonic solar cells, which have in principle have opportunity for lower cost at the cell level. And then, of course, if we think about multi-junction cells on a per area basis, they're not even on the chart. They're at of the order of thousands of dollars per square meter, tens of thousands of dollars per square meter. But of course, concentration brings them back such that the cell-related cost per aperture of the concentrator system brings them back into competition on the chart. And if we think about other novel and future forms of photovoltaic materials and devices, in general, I would assert that they would have to lie somewhere in this range, because unless they can compete favorably with technologies that have a head start, like crystalline silicon and thin films, and offer increases in efficiency or lower cost, it will be a daunting task to bring them to practice. But that's a sort of overview sketch. And one of the things that also comes into play here is the fact that there is no solution at the origin here where we can reduce the cell cost per unit per area cell cost to zero at vanishing efficiency. Because there's a finite balance of systems cost that's incumbent on any photovoltaic system that's independent of the absorber, and it's going to be very challenging to get this below the order of $50 per square meter which means that practically things that are fabricated need to lie on this or need to have efficiencies that are compatible with this added cost per unit area. So when we think about thin films, the thin film materials that are conventionally that are commercially available are cadmium telluride, copper rhodium gallium diselenide, polycrystalline silicon, and amorphous silicon have efficiencies that are lower, and part of that is due to the microstructural features in the cell that limit their efficiency. And one of the things that is a common feature of the polycrystalline thin films is the presence of grain boundaries. And if grain boundaries in a thin film cell intersect the cell in sufficiently high density and have recombination centers at the grain boundary at sufficiently high density, they can render the areas of the cell here where that are shaded as dark regions here as regions that are effectively inactive because they represent regions where photogenerated charge carriers are trapped, and the trapping of charge carriers competes with photocarrier collection at the PN junctions. And fortuitously, some of the materials like cadmium telluride and copper rhodium gallium diselenide have materials that adjust their point defect populations in ways that enable the grain boundaries to be much less recombination active than they would be in other semiconductor materials in polycrystalline forms. And in the case of polycrystalline silicon, a lowered recombination activity can be achieved by extensive hydrogen passivation, whereas without hydrogen, the recombination activity for the density grain boundaries depicted here, where the grain boundary density is greater, say, than the film thickness, would be unacceptably high. And of course, amorphous silicon is a device material that's quite different in many respects in terms of its transport properties, but by virtue of being very hydrogen passivated, enables carrier collection over the physical thickness of the cell to enable a photocurrent and photovoltage to be sustained. Now, for the case of polycrystalline thin films, one prominent example of what's achievable is embodied in this work that was reported first by Kanika more than 10 years ago. And this represents a microcrystalline silicon film that's extensively hydrogen passivated, and in the process of hydrogen passivating grain boundaries and also texturing the surface of a thin film whose thickness is of the order of a few microns thick, the cell efficiencies greater than 10% were achievable. That has not translated into cells of this efficiency in manufacturing. Kanika is, in fact, a photovoltaic module manufacturer, but this is an example of what's achievable in the lab for passivated microcrystalline silicon films. Another very interesting example is work done by CSG, crystalline silicon on glass. Is a company that came out of the University of New South Wales and situated in Germany, and developed a very interesting technology for thin silicon films. Also extensively hydrogen passivated microcrystalline silicon with an innovative contact structure to the absorber layer, and it embodies many of the features that one would want to prevent surface recombination, such as a back surface field and amorphous silicon passivation of the front surface. And in this case, for the microcrystalline silicon, similar efficiencies were achieved. So this is an example of the kinds of things that can be achieved here at the, this is called a mini module. It's of the scale of perhaps a large crystalline silicon solar cell. So for amorphous silicon, this is an example of what's available in the marketplace today. Modules, for example, from Kanika, as I mentioned earlier, have a module efficiency of 6.5%, and from United Solar, located here in the United States, also similar module efficiencies, and these are stabilized efficiencies that have undergone the light-induced degradation due to the well-known Stabler-Wronski effect that leads to an enhancement in the recombination activity in amorphous silicon under light soaking. And so that's sort of the status, and by this measure one would say that amorphous silicon looks like it's in danger of falling below the efficiency threshold where photovoltaic devices can merit insertion into a module. There are developments on the horizon in the amorphous silicon thin film arena with lower hydrogen concentration and, for example, a recent report from the Oerlikon Solar and University of Neuchâtel laboratory in Switzerland of 9.5% efficient cell in amorphous silicon. So I think the end game has not perhaps been played yet for amorphous silicon. One direction to go, and this, by the way, this cell takes advantage of extensive light trapping. The cell is deposited on a highly textured glass substrate. It's a glass substrate that's coated with a back reflector and of silver and zinc oxide to make contact to the cell. And that plays a very critical role in enhancing the photocurrent and bringing it up to enable this kind of efficiency. And one of the questions that's currently being asked is the question of whether or not this light trapping effect is optimal. Eli brought up the fact that we now know that light trapping in the ray optics limit is, the limits are well established, but they're not known for in the thin film limits. For example, here's an example of a periodic structure made by nanoimprint lithography in which periodic arrays of a similar silver and zinc oxide back reflector are applied prior to growth of an amorphous silicon solar cell. And for this particular structure, the photocurrent, the short circuit currents that are achievable exceed the short circuit current densities that are achievable using randomly textured glass surfaces coated with silver and zinc oxide, as is the current industry practice. So I think this points the way to the future for enhancing the photocurrent of amorphous silicon cells. It's not known how close this structure is to the optimal structure, and again, as Eli pointed out, that's very much an open question. What are the fundamental light trapping limits? And I point out that in this case, the cell is extremely thin. We're definitely in the wave optics rather than the ray optics limit in terms of the light trapping within such a thin photovoltaic cell. So this looks like a rather sophisticated nano fabrication process. It's done using a nanoimprint stamp lithography process, and this is now, there are a number of companies that are offering such pattern structures on long tens, hundreds of meter roll structures with apparently low cost. So this looks like it may not be that producing textured light trapping structures may not be merely a laboratory curiosity. So amorphous silicon also, that light trapping is being used in tandem amorphous silicon cells in interesting ways. Here's an example of what's called an asymmetric intermediate reflector, in which a light trapping structure is inserted in between a high band gap amorphous silicon and a low band gap amorphous microcrystalline silicon cell. And the structure is designed in such a way that high energy photons are trapped within the high band gap amorphous silicon cell, and low energy photons that are transmitted have a high probability of total internal reflection at this asymmetric reflector, and offers some degree of spectral splitting by the insertion of this asymmetric reflector layer at the interface between the two cells of the tandem structure. In the area of polycrystalline copper-indium gallium diselenide, these are sort of examples of what is available commercially at the moment. It's possible to obtain thin films on various flexible sheets. For example, Global Solar here in the United States and Worth and Solarion in Germany are making SIGS films on, and there's a very active set of early stage companies working on SIGS thin film solar cell development with cells in the in manufacturing here in the 7 to 9%, or excuse me, modules in the 7 to 9% regime. SIGS has been one of those beguiling materials where the lab records that have been achieved at NREL and other places, for example here without an AR coat, have shown great disparity relative to the achievable efficiencies in modules, and it appears that the complex multi-component microstructure of the film has an inhomogeneity in the open circuit voltage at the scale of things that are just larger than the laboratory cells that has a significant impact on the achievable open circuit voltage over large area module-like arrays. And so as a result, for example, companies like NanoSolar, which originally championed the notion of depositing SIGS films on large area web-like substrates and making essentially a module level cell structure, have chosen instead to enjoy the efficiency benefits of segmenting their foil into module-like or into cell-like coupons and then binning them, similar to the practice that's done with wafer-based photovoltaic devices, and then, which are then assembled in modules in a conventional stringing process. So it's making materials that are uniform over large areas is a challenge for truly thin film photovoltaics technologies. So for silicon of the kind that I was describing earlier, one of the things that's interesting about this is the fact that there is no optimal grain size, and the optimal grain size in a silicon photovoltaic device depends extremely sensitively on the state of recombination of activity of the grain boundaries, here expressed in terms of the surface recombination velocity between 10 to the 7th and less than 1,000 centimeters per second. And you can see here the open circuit voltage numbers for various types of thin film polycrystalline or microcrystalline silicon solar cells as a function of grain size are all over the map. You can see examples where the grain size approaches macroscopic dimensions, what you would call multicrystalline silicon, and down here where it's truly nanocrystalline. And there's not a dramatic trend that follows one of these dotted lines here. That's because they all exhibit different levels of recombination activity. And so that has given rise to a situation where microcrystalline silicon cells have become a standard part of the amorphous silicon heterojunction solar cell technology, and there hasn't been a strong push to increase the grain size, or hasn't been a method, a viable method identified to date to do that. These open circles represent extensively hydrogen passivated structures where hydrogen passivates the grain boundaries very extensively, and you can see the surface recombination velocities of these are relative to these iso recombination curves are low. And then these are examples of materials that were fabricated, and perhaps a little bit of hydrogen was added after the fabrication process. The materials were made by either melt growth or solid phase crystallization, and a little bit of hydrogen was added at the end, but that doesn't allow nearly as extensive hydrogen passivation. So the only solution to lowering the recombination activity of grain boundaries is to lower their density and to improve the open circuit voltage. And so that's this is actually a plot from a few years ago, about 6 years ago, from Jürgen Werner, and the situation is largely the same today. But I think we can suggest that perhaps an ideal type of thin film silicon structure would be one that had the surface recombination activity properties of these films, but grain sizes in such that the open circuit voltage could reach this broad plateau, which is in the range of 10 to 100 microns in grain size. So that's still an open challenge as far as I know. So if we think about carrier recombination in polycrystalline films, You can think about this in terms of just the device physics models that Dick Swanson was talking about. And if we conjure a model here of a PIN or PNN plus solar cell structure, and we now permeate this with vertical grain boundaries that intersect the junction, normal to the junction, and we develop a model for donor and acceptor-like traps that's a relatively conventional model for grain boundary traps, which are exponentially distributed in energy. And we assume also features of the bulk like doping-dependent mobility, and then we solve the device physics and transport equations, coupling the electrostatics to the transport. We can now do sort of a sensitivity analysis of what affects the transport and the open circuit voltage in such a cell. And so one of the things that you can see immediately is that longer bulk lifetimes increase the minority carry current flow towards the boundary. And that basically says that if you have good quality material, the variation in the carrier excitation population due to the presence of a sink is more sensitive to the presence of the grain boundary if it's not already being overwhelmed by bulk recombination. And that shows, for example, here in the case of silicon with a microsecond lifetime versus 10 nanosecond lifetime in a thin film. Similarly, if we were to look at the trend in open circuit voltage and a similar trend in efficiency for recombination activity with 10 nanosecond lifetimes or microsecond lifetimes, you can see that the better the bulk material, if the material has a longer bulk lifetime, the more sensitive it is to grain boundary recombination. So, for example, you're sensitive to grain boundary, the open circuit voltage, and the efficiency. So you can see the efficiency is almost exactly tracking the open circuit voltage. Carrier collection is still relatively efficient in both cases, but the efficiency is tracking the open circuit voltage. And and this is happening at, here, for example, grain boundary trap densities of 10 to the 13. So that's essentially one site in 100 at a grain boundary is populated by a trap site deep within the band gap. So that's quite a high sensitivity at which the open circuit voltage begins to degrade. So one of the solutions for this in a polycrystalline thin film is if you had high lifetime material, would be if you could heavily dope that material without the dopant itself also adversely affecting the bulk recombination lifetime and diffusion length, you then flatten the electrostatic landscape. So, for example, for a lightly doped silicon structure here at 10 to the 15 doping, you can see there's considerable variation in the space charge across a grain boundary here. Here's the PN junction. And if the doping density goes up to 10 to the 17, you can see here this landscape becomes very flat. The space charge region is confined to the grain boundary. So in that, all things being equal, until the onset of doping effects that lower the bulk diffusion length and lower the mobility, there's a benefit in polycrystalline films to increasing the doping level so as to flatten this electrostatic landscape and confine the trapping sites essentially to a space charge region that's progressively or proportionately smaller around a grain boundary in a heavily doped structure. So I wanted to also mention that there has been a lot of thought about making thin films of essentially single crystal materials. And so here's an example that's currently getting a lot of press at the moment, which is to use a implantation-induced exfoliation process. This is done by a company called Cygen that is trying to solve the problem of the so-called kerf loss in silicon wafer manufacturing by being able to delaminate thin silicon films of the order of 10 to 20 microns thick by first weakening a subsurface layer and then peeling it off using mechanical forces. Other approaches that have been taken to making thin cells include growing on porous silicon, for example, and etching away the porous silicon, making by liquid or vapor phase epitaxy templates that allow the entire lattice work structure like this so-called epilift structure from Australian National University to be then etched away from the substrate. So you can take this entire sort of trellis-like structure off the substrate after it has grown as a single crystal on this templating substrate. Another approach, of course, in the last few years has been to take advantage of the dramatic cost difference between a metallurgical grade silicon wafer and a Czochralski grown wafer made out of solar grade polycrystalline silicon, and to simply make what's called upgraded metallurgical grade silicon by growing an epitaxial film in some way that minimizes the impurity cross-contamination from the metallurgical grade silicon into the epitaxial thin film. So this is essentially used as a wafer, but the argument here is that the cost of this wafer is so low that that makes it effectively a thin film process. So then you can develop a sort of taxonomy for silicon photovoltaics of films ranging from amorphous to microcrystalline to polycrystalline to structures that are thin such that they perhaps exhibit incomplete light absorption without extensive light trapping, up to thin wafers to thick wafers, and then there's a corresponding increase in efficiency as you go towards more crystalline and thicker structures. This sort of process can also be done for the compound semiconductor materials. This is an illustration of hydrogen-induced exfoliation for a germanium layer, and that germanium layer can be used as a template for growth of multi-junction solar cells. Here's a growth of indium gallium phosphide gallium arsenide cells grown on a germanium substrate and then exfoliated and then bonded onto another low-cost handle substrate. And the efficiency and the light-induced IV and quantum efficiency are very similar for these structures as for wafers, as for cells grown on wafers. So this represents potentially a way to peel off thin films from thin wafers. This can also be done for example, indium phosphide as well as gallium arsenide and germanium. Here's an example of an indium gallium arsenide cell peeled off and then bonded onto a silicon wafer. This similar process can be done in which gallium arsenide layers are peeled off of their growth substrate and then bonded onto a handle substrate. And in fact, the thin film efficiency record is currently held by the University of Nijmegen in the Netherlands for a gallium arsenide thin film cell. Truly thin. It's a thin cell that it would, in the absence of a back reflector, would be semi-transparent and has an efficiency of 26.4%. So a lot of what's visible about the photovoltaics industry nowadays comes from one company in particular, and that's First Solar, and they have made a remarkable strides in lowering the cost of polycrystalline thin films. And for example, here's an announcement about the building of a several gigawatt, 3 gigawatt installation on the edge of the Gobi Desert that will take place over the next few years in China. Uniquely among the thin films, this sort of level of production is now one that's being achieved by many of the crystalline silicon companies like SunPower, Suntech, and Sharp. But this uniquely among the thin films, First Solar has been successful in scaling manufacturing of cadmium telluride thin film photovoltaic devices. And so that's certainly something that has caused people to stand up and take notice. And by virtue of their very low cost per watt for manufacturing, despite the considerably lower efficiency than exists for crystalline silicon thin films. And so the efficiency records for cadmium telluride for First Solar's devices, they're in the 9 to 10% range. The record efficiencies, however, are in the range of 15 to 16%. So there's a similar story for cadmium telluride as there is for copper indium gallium diselenide, which is that the Champion small area cells have considerably higher efficiency than the cells made at module scale. And that's likely due to inhomogeneities in the structure. One thing I would point out is that cadmium telluride cells are inherently heterojunction cells that using a p-type cadmium telluride and often a n-type cad sulfide and zinc oxide top structure, unlike silicon cells, which are typically but not uniquely homojunctions. So one of the issues with cadmium telluride, of course, that has come up, and it was a subject of very lively discussion at the most recent Photovoltaic Specialist Conference and other places, is the resource availability of the elements that make up the thin film. So, for example, we perform the following thought experiment: construct a terawatt of photovoltaics consisting of optically thick cells at a 15% efficiency, and we look at this chart here, which depicts the elemental abundance in the Earth's crust as a function of atomic number for the various elements in the Earth's crust. Here, of course, the rock-forming element silicon, which is one of the second most abundant element in the Earth's crust, and many of the other mineral-forming elements. You can see that the materials that have been chosen for thin film seem to have been chosen with blatant disregard for abundance, and that's, of course, reflects the fact that when the technologies were developed, photovoltaics was a fledgling industry and people weren't really thinking about bumping up against resource limits. So one approach to addressing this may be to go to very, very thin cells. So, for example, so one approach, by the way, is to develop mineral-like semiconductors. And as we mentioned earlier, the cadmium telluride is an example of something that forms a heterojunction cells, and many of these mineral-like materials exist and are, in fact, semiconductors. For example, copper oxides, zinc phosphide, iron disulfide, and have direct band gaps and have respectable mobilities, but they're quite difficult to dope with both doping concentrations, doping types at high doping concentrations, and but like for copper indium gallium diselenide and cadmium telluride, it seems feasible that it might be possible to make heterojunction technologies with these. Another approach, of course, is to utilize the opportunity to make thin film cells and light trapping to dramatically lower the thickness, and I think those engaged in the thin film cadmium telluride and copper indium gallium diselenide are keenly addressing that challenge. So if we think of resource abundance from another point of view, though, not just looking at the elemental abundance in the Earth's crust, but we look at production and reserve numbers, for example, tellurium, and it comes primarily as a byproduct of refining, smelting copper, or recovering copper ore, and the at an annual production that was characteristic of what it was in the year 2000, the yearly use of tellurium did not bump up against either the annual production in thousands of tons per annum or the overall reserve base. But you can see here, if an industry could grow to a scale of 50 gigawatts, then you can see here that relative to what's currently projected to be the reserve base available by extractive metallurgy of copper and zinc, would allow for about 9 years of photovoltaic production for cadmium telluride. So this is it's I think very much an unresolved issue, but I think even those in the industry realize that resource abundance for tellurium and indium particularly are going to be limited by recycling and alternate sources rather than primary extractive metallurgy from the conventional streams for those materials. So that suggests the opportunity for looking at Earth-abundant alternatives to those semiconductors. And this is a paper by Cyrus Wadi I'll direct your attention to, which is an assessment of the availability of various compound candidate photovoltaic materials here from less abundant to more abundant, with these dotted lines representing the worldwide consumption of materials that would be necessary to sustain, for example, all energy production in the world, which is probably a gross overestimate of the need for photovoltaics, or, for example, U.S. energy consumption here. And you can see that semiconductors like, for example, gallium arsenide, zinc oxide, copper, zinc, tin sulfide, and lead sulfide, copper oxide, and so forth are sufficiently abundant not to be running up against likely resource limits. So speaking of copper, zinc, tin sulfide, this is an interesting material where there's been rapid progress made, coming mostly from IBM using, this is essentially an analog to the 136 chalcopyrite structures, where now a combined composite group 2 4 6 structure is used here. So indium is replaced by essentially a valence, average valence of 3 from zinc and tin, and cell efficiencies of 6% have been realized here, and more recently up to 9% in the lab by the IBM group. And this looks like a very interesting, there's still many complex issues, but it looks like this is a direction of very active research for those working on the chalcopyrite compound semiconductors. So I'll just sort of motivate here an example of a material that is a potential alternative to some of the existing photovoltaic materials like cadmium telluride. Like cadmium telluride, zinc phosphide is a material that can be congruently evaporated. By the way, that's the thing that accounts for the impressively low manufacturing cost for cadmium telluride, the fact that the vapor can be sublimated in essentially in molecular form and deposited by convection of that vapor. This is how First Solar does the deposition process. Convection of the vapor across a cold glass sheet, enabling module scale deposition of films in a matter of tens of seconds. So the ability to form to congruently evaporate the cation and anion seems like a very powerful advantage for that kind of process. Similarly, zinc phosphide is a material where this can be done. This is an example of some work on growth of zinc phosphide. Zinc phosphide is an example of it is almost a case history of, or microcosm of, the photovoltaics industry, where the early work was done in the early 1980s, and then the budget turned down, and there were strategic decisions made by the solar energy program to focus on a few thin film materials, and other alternatives like copper oxide, copper sulfide, zinc phosphide, and so forth fell by the wayside. And but this is a material that's a direct band gap of about 1.5 EV, and cells were made back in the 1980s with efficiency of about 6%. So recently, here's some work on evaluation. This is an area where I think progress is going to require electronic materials research, very fundamental electronic materials research. For example, the band gap until recently was incompletely known. This is a material for which the direct and indirect band gap are relatively close, and it's just like germanium, for example, it's just barely an indirect band gap material. And so this allowed us to reevaluate the band gap of zinc phosphide. And that kind of basic electronic materials research is going to be needed for these mineral-like semiconductors going forward if they're to represent alternatives to the candidate thin films that we have available today. So I just thought I'd mention at the end here some discussion about excitonic solar cells. There are a number of EFRCs that are working on organic and small molecule and fullerene and mesoscopic injection, so-called dye-sensitized cells. And we can think about, these are all materials characterized by low dielectric constants, so the photoexcited carriers exist as excitons. But most of these materials, for example, exhibit relatively high absorption coefficients. So despite the fact that the exciton diffusion lengths are extremely short, it's possible to collect light at least in the region where the molecular species are absorbing in a structure that's optically thick. And for example, by using a bulk heterojunction where the two collecting semiconductor materials are ramified in an intercalated structure to enable very short exciton transport lengths, it's possible to collect the excitons relatively efficiently. Another approach that's been taken is to incorporate inorganic structures like nanowires of inorganic materials to act as collecting agents that where one of the carriers can be collected with higher mobility, typically the whole, which has lower mobility in such hybrid inorganic structures. So this is an example of what's been achievable to date in bulk heterojunction cells. This is a polythiophene PCBM cell made at NREL, about 4% efficiency. This doesn't represent a current record. The current record cells are in the north of 7% efficiency, but I think it represents sort of a typical result with these widely studied semiconductor materials. And it's interesting to think about this in terms of the ideal diode equation and think about what the disparity between the current densities, voltages, and so forth that are seen in these materials relative to what's expected. And so, for example, relative to the ideal diode equation expectation for a band gap of 1.9 eV for these materials, the current density is about 61%, but the voltage is only 38%. So you can see there's a huge challenge with voltage in these cells. The current collection is actually pretty good for a cell that's very thin. Fill factor is not too bad, but it's the voltage that's really poses a challenge for the organic materials. And one of the reasons for the challenge in the voltage is fundamentally related to the heterojunction. Well, so one of the so the current density of many of the organic materials is related to the absorption of molecular species, which span typically a narrower range of the solar spectrum than many of the inorganic semiconductors with band gaps in the 1.1 to 1.5 eV range. Here's, for example, the absorption spectrum of polythiophene here overlapped between about 350 and 600 nanometers. There is considerable activity at trying to develop organic semiconductors that have lower band gaps to access the red part of the and near infrared part of the solar spectrum, and that's a subject of current active research. So I mentioned that the significant disparity between the open circuit voltage in polymer heterojunction and organic cells and the diode equation limit. And it's illustrated here by the fact that in this bulk heterojunction here, for example, between PCBM and polythiophene, once we absorb across and create an exciton across the polymer band gap here, these represent the energy levels relative to vacuum. As the exciton dissociates, the electron relaxes over a large distance, and so the open circuit voltage is limited to be no more than the energy between the energy separation of the hole and the electron. So essentially we're paying a very large penalty here by the injection of the electron across the heterojunction. So the good news is that the exciton dissociation probability is close to 100%, but the bad news is you used an enormous voltage to do that. The directions for research in this area, and there's a lot of thought and activity in this area, is to try to develop heterojunctions whereby this disparity and this very large band offset here at the heterojunction can be lowered. So, for example, if you could lower, not change the band gap, but by manipulation of the interfacial energetics, lower the energy levels of the entire semiconductor, that would enable the absorption spectrum to remain the same, but lower the energy relaxation that is experienced by the electron as it's injected into the across the heterojunction, thereby increasing the open circuit voltage. So I think that's an interesting direction and a challenging direction for the future. So in summary, thin films have made impressive strides recently in understanding and also in large-scale fabrication, particularly in the case of cadmium telluride. Efficiency is very much a critical discriminator, so I'm complete unanimity with the previous speakers. And because of the complex microstructure, understanding of the efficiency limiting processes is very critical to progress. And that's something that the efficiency limiting processes are related to heterogeneous defects, compositional inhomogeneities, and features that are present in polycrystalline thin films, and thin films in general. And so those are all areas for future scientific research that can make thin films reach the efficiency levels that will allow them to compete with, for example, crystalline silicon in the far future. So thanks for your attention.